Here I will teach today orbital angular momentum (LM) and also discuss about raising and lowering operator of angular momentum. So let me write. Angular momentum Lm and ladder operators. So as we know, the angular momentum is defined as r cross p. You know it well, right? If I split this angular momentum into its component expression, so we will find like this. Suppose for Lx, so it will be like ypz minus zpy, and similarly Ly will be zpx minus xpz. Just look at the formation that we have. If it is x component of angular momentum, then the term will be consisting of y and z component of having spatial coordinate and momentum coordinate. You can look at. So thus also the Lz will be simply x with x and y component, x py, right, y px. Fine. So to find out values of Lm, conclusion about to conclude the values of Lm, first we will find the commutation relations of these angular moment components. Okay. So let's find it. Suppose Lx, Ly. Okay. So I will replace those terms, as you can understand. Pz minus z py Lx, right, and Ly will be z px minus x pz. Fine. Now I will expand this thing. Just by expanding and applying all other relations, commutation relations, canonical commutation, those are called canonical commutation relations. So we will find, just I will write into it pz px minus, okay, first this was done, and second I will treat it with this, okay, so y pz and x pz. So similarly next term z py, okay, so z px, and finally last term z py x pz. Fine. As we know that from the commutation relations that those all other terms except x and px, y and py, and z with pz. So except these three terms, all except these, all other all other combinations commute. So that means if you want to get commutation relation of suppose py and pz, it will give 0. But only z with pz and these two terms, these two combinations will not give 0 value. Okay. So fine. So from this conclusion, we can look at the term in the second and third term. Suppose if you take term pz, then you will get xy, commutation relation of xy. So this will give 0, and also this will give 0 if you take common of z. So py and px commutation. So we will left with these two terms. Okay. So we will be left with only y pz z px, fine, and plus z py x pz. So all other term will so two other term will give 0. So I will not do all the rigorous calculations, just I will write the result actually. So here you will get, if you break all this or expand this equation and reform the equation, so finally you will get like this equation. You can do yourself. So x py, right, z pz, this like equation. So from there putting the computation values, the values of the relation, I can get x py first, because this will give positive value and this will give negative, because this pzz, if it were zpz, then it would give positive value, but it is just reverse thing. So y is like that. So you can look at this expression. This expression, you can see this is actually Lz. So are you right? So what we have got? So finally we have got I h car Lz. Right. So please remember those computation relations, because in exam you can be asked to calculate this simple computation relations for short questions. So similarly, what we will get? Similarly, suppose Lz, you can understand. It will give just clockwise. Replace it clockwise, right? Suppose it is Lx, it is Ly, and it is Lz. So you go like the cyclic order. So it is Lx, Ly, it will give Lz. Okay. So Ly, Lz, it will give Lx. Okay. So similarly, you can understand if it is Lz, Lx, not Lx, Lz. If you write Lx, Lz, then you have to write minus ih car Ly, right? But you have, if you write in this form Lz, Lx, then only you can write Ly. So fine, you have got these commutation relations. Fine. So fine. So then we will from this commutation relations, since you have got this commutation relations, so you can calculate the uncertainty principle. From the uncertainty principle, you can calculate the uncertainty value of delta Lx, delta Ly, because if you look at the generalized uncertainty principle, so from there you can find this type of value. Because now let me write so that you can understand that my statement, what I am going to tell. And there is something relation, sorry, Ly, suppose it is Ly, right? So this has been given like that. So this is the commutation Lx, Ly, like that. Okay. This is like that. So if you put the values of Lx, the computation value of these two, so you can get the this uncertainty values, right? Generalized uncertainty principle. Fine. So this is not the point of discuss. So I will go into the main point. So now I will try to calculate. Suppose this is. No, I will not try actually. I will try to find out that whether this L square commute with the other components of angular momentum, that is Lx, Ly, or Lz. So first let me find out, because these are required for finding out the ladder operators. So you will understand if you follow me. So Lx, now I will break, right? Distance plus Ly square, okay, Lz square Lx, fine. So fine. So now you can understand here, since it is Lx, so this two will commute because they are same, Lx and Ls component. So I have no problem with this. This will give simply 0, but I bother about these other two terms, right? So suppose this term. So this term Lx, that means it is Lx, right? So if Ly. So if I break this, expand this, I will get Ly, Lx, Ly. Similarly, all these Lz, Lx. So Lz, Lx, Lz, like that. Okay. So if I put all the values, computation relations, minus ih cut Lz plus, so these are actually just simple calculations, nothing else. There is no hardcore physics. Just write this thing, and this one ih cut So this is a y way with a bracket. Okay, fine. These are fine, and if you see, this will give 0. Fine. So we have got this thing. So now we can conclude that L square also commute with all the other components. So L square Ly will give 0, and also L square Lz, so Lz will give 0. Fine. So in the compact way, we can write, that implies we can write L square L equals to 0. Here L are all other components 0. I can write in this way. Now that main main point, we will come into the main point. So we can write, suppose if suppose psi is the wave function or eigenfunction. For that, since we are dealing with the operators, so we will call it eigenfunction. Okay. So let's say that eigenfunction like that L square. Let's assume L square. Suppose that eigenfunction is let me define the eigenfunction as S. Okay, S. So it will let me define eigen with eigenvalue S. And similarly, let me define Lz. So Lz will give also its eigenfunction because they commute with each other. So it will operate on the same eigenfunction. So that's why we have done this kind of calculations to see the actually whether these components of angular momentum commute with L square. So we can conclude like that. Fine. This is fine. Okay. So now we will do the same algebra, same like not the same actually same, but something same like we have done in our harmonic oscillator problem. So let us define operator L plus minus, suppose like that, Lx plus. This is a little bit simple because there the formation was a little bit was tricky. We had to find out that associated equation. From there we had to conclude about the operators and ladder operators. Now here it is a little bit simple. So it is Lx plus minus Ly. Fine. So now we will see that is this operator commute with Lz term. So let us write. So is Lz commute with L plus minus. So for that we have to find out Lz L plus minus. So fine. So Lz Lx you can understand. So Lz Ly. Right. So plus minus. Directly I will write Lx plus minus Ly. Okay. So fine. So again it is plus minus h cut L plus minus. Okay, fine. So fine. We have got like that, and for suppose L square L plus minus. So you can understand since this L plus minus consists of only Lx and Ly, and since Lx and Ly commutes with L square, so this definitely will give 0. So fine. So now if it is 0, and also we have seen Lz in commutation relation with Lz, and L plus minus is giving only L plus minus. So we can say that F and S can also be eigenfunction of L plus minus. So we will find that thing. So we can say S is also eigen function of L plus minus, because it commutes with this, right? So fine. So now we will try to find L plus minus S, right? So so let us first find L square, because we will apply that thing there. Okay, so L square L plus minus S. So since it commutes, so it can be written S plus minus L square S. Okay, so it is written as, suppose, L plus minus lambda S, and so lambda L plus minus S. Fine. And also we can find Lz, L plus minus S. Okay. Now see, we can write this thing as Lz L plus minus L plus minus Lz S plus L plus minus Lz. Yes, just I have rearranged the thing. Just I have included these two terms. Okay, so from there you can understand that this thing is actually the commutation relation of Lz L plus minus, right? So this thing I can write L plus minus S, right? Plus again L plus minus, and Lz on S already we have defined mu, right? Yeah. So already we have defined this thing. Yes. Fine. Sorry, previously I have F, it is S. Okay, so that was wrong. So fine, this is fine. So we can write this thing like mu plus minus h car L plus minus S. So now we can understand that if we operate Lz on L plus minus S, and if we treat this thing as the eigenfunction, then we will get eigenvalue of this. So here is the things I mean the similarity with the previous we have done in the harmonic oscillator. There we can also see that on operating a plus if we consider that eigenfunction, we have got some this type of eigenvalues. That is, if this is something increasing or raising this eigenfunction with the increasing or decreasing eigenvalue. So fine. So that's why they are called raising and lowering operator. This is L plus is raising operator and L minus is lowering operator. Okay.